Good day. My name is Lara Van Niekerk. I work for the Council for Scientific and Industrial Research in South Africa, and I would like to tell you about the vulnerability of South Africa's estuaries to climate change. South Africa is a developing country. We resource limited, and we have very little regional and individual information in our estuaries. I'd also like to draw your attention to my co-authors, Stephen Lamberth, Nikki James, Janine Adams, Susan Taljaard, and Andre Tron. What do we know about our systems is we've got about 300 estuaries in South Africa, spread all around the coast. We have got 3 to 4 biogeographical regions, cool temperate, warm temperate, and subtropical. And right here at the top, we've got a transitional zone going into tropical, another transition zone here, and then a transition zone between cool and warm temperate. And as you can see from this, most of our systems are smaller than 50 hectares in size. We also know that we are seeing changes in the sea circulation patterns, with the northern, this Agulhas current become intensifying, and the southern current starting to slow down and meandering more. We're also starting to see some cooling around the Cape South coast and some warming in areas of the Agulhas current. In terms of the projections of change for our country, we're generally looking at a warmer and drier climate. It's between 2 and 4 degrees increase in temperature is predicted, with some months going up by 5 degrees. We're seeing a shorter and more intense summer rainfall season, and overall this rainfall region of South Africa is projected to become wetter during the summer. There'll be a drier winter rainfall area and a more intense rain events all around. In terms of sea level rise, while global sea level rise is projected to increase roughly 3 millimeters per year, in South Africa, we estimate it's between 0.5 and 2.7, which is up from earlier projections. In terms of storminess, we know the increase in air temperature will lead to an increase in sea surface temperature, which will lead to an increase in storm surges. Conservative estimates is a 6% increase in storminess. Will lead to a 10% increase in wind speed and a 12% increase in wind stress. Overall, 26% increase in wave height and 80% increase in wave power. In most cases, we're looking at a potential increase in winter, increase in storminess, and a decline in summer. Acidification, we think that the pH is likely to decrease between 1 to 3.3 units. But what we have is a natural buffering that on our west coast, we have intense upwelling events, which in any case bring up low pH water. And we also have quite a high number of low pH rivers and estuaries. Responses to climate change. We see changes in runoff, will change our coastal connectivity, our estuary mouth conditions. We'll see modifications in the intrusion of salinities and even groundwater in systems. Changes in the biochemical inputs like nutrients, changes in sediment processes, and changes in the contaminant behavior, becoming either more or less depending on what would happen to the rainfall. Sea level rise will also see a change in salinity penetration and groundwater. We'll see changes in coastal connectivity, estuary mouth state, coastal inundation, coastal erosion with loss of some beaches, and potential loss of blue carbon ecosystems due to coastal squeeze. An increase in frequency and intensity of coastal storms is likely to decrease coastal connectivity, increase coastal erosion, loss of beaches, and coastal inundation. Ecological responses to climate change stresses range from changes to the ocean circulation patterns with species distribution. Steve Lamberth recorded range extensions of over 1,000 kilometers thus far. Larval and egg survival will change with the current changes. Rising temperatures will cause species distribution changes, arguments like mangroves, and ecosystem structure will also change. Ocean acidification is likely to cause problems for calcifying organisms and it might delay metamorphosis in some of the planktonic ocean life history stages. So then moving forward, I'm not going to take you through the detail of this, but like I indicated before, we divided our coast up into the different biogeographical regions and the transitional areas, like that is transitional area. And then we looked at what the different changes mean to that part of the coast, also looking at the dominant geomorphology and the type of estuaries occurring there. Blue colors mean an expected large degree of change. Light blue means somewhat of a change, and low or light blue means there's very little change. It's very similar to present. So we ran through the different drivers of change, trying to understand the direction of change for our systems. And you need to keep your eyes on the blue colors here, the dark blue colors. For argument's sake, here an example of temperature changes, we see the land temperature regime being significantly changed, and therefore driving along shore, and the Gullis current driving along shore gradient changes as well in this part of the coast. Coming to precipitation, you're starting to see the overwhelming South African picture, with the biggest amount of change happening on the west coast, and in the subtropical region, with the west coast going drier, in the subtropical region becoming wetter, and leading to all kinds of changes in landscape connectivity and salinity regime, with these estuaries closing more and these estuaries potentially increasing connectivity. Also seeing more increase in inputs on this coastline, sediment and biogeochemical signals, where there is a decrease and the related biological response. In terms of ocean acidification, this is an upwelling coast, so this is the coast that will mostly be exposed to ocean acidification. In terms of sea level rise, the pattern is slightly different. In terms of the coastal topography, we're seeing quite a bit of a change here, with likely more salinity penetration and overwash occurring in these parts of the coast. And then increase in storminess. This part of the coastline is actually already quite exposed. So the estuaries tend to be more perched, especially around this part of the coast. We therefore think the most likely impact will actually be on the parts of the coast that's less exposed, and more likely to see the increase in overwash and salinity. So therefore, we took the whole picture together, and then what you start seeing is that there's significant structural changes expected along the west coast and the subtropical KwaZulu-Natal and even tropical regions of the coast. And although there's some distribution changes happening along the east coast, most of the structural changes is happening around this part of the coast. So overall, we know that the cool, temperate and subtropical coasts face the biggest physical changes, possible niche changes in advancing generalist and opportunistic species, with coastal connectivity changing quite significantly, biochemical signals changing, and shifts in sediment loads and beaches. The transitional zones, especially the west coast and south coast, are most vulnerable to land and sea temperature changes, with species range extensions expected to carry on, while the upwelling coast is subjected to ocean acidification and low DO events. Blue carbon habitats are under stress from sea level rise all around the coast due to coastal squeeze and natural topography which don't allow for retreat. And increased storminess holds the risk for sandy beaches in estuaries and sediment-starved areas. Our key challenge is that we need to downscale and better get a handle on the drivers, although our knowledge in this aspect has grown quite a bit. For us, one of the key things is the downscaling of the global and regional models to the primary catchment scale and into runoff to the estuaries and coastal environments. We also need to move now from this regional approach to the estuarine ecosystem state change, and evaluating also some of our resources and species. For instance, we have to look at the small temporary open estuaries as a group or river-dependent offshore ecosystems. We also have some shortage of some of our fundamental data sets. Our coastal topography and LiDAR bathy data needs to be sharpened. We need to look at remote sensing tools, including the automation, monitoring aspects of it. We especially need to focus on the links between things like runoff to sediment supply, land-sea connectivity, salinity biochemical regimes, sediment processes, and then obviously the key biotic responses, all constrained by these very old data sets. And then one of the things for us is being a high variable coast, we actually need to understand the medium to long-term biophysical cycles, the natural cycles, and where the climate change regime is leading us. And most of this we have captured in the National Biodiversity Assessment. I refer you back to that document for further details. Thank you.